Welcome to AP Chemistry. In this video, we will derive the gravitational force equation and the electrostatic force equation in order to see their inverse square relationship and begin to posit possible analogies. I assume that you have encountered the idea posited by Galileo that objects that differ in mass, in the absence of any air resistance, will accelerate by the Earth's gravitational pull at exactly the same rate. After watching the next video, we will derive some important relationships.
Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
We dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCB 30-1, pressure set point at 240 psi. ER, go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Look at that.
They came down exactly the same.
Look.
Look how they hit right there.
Exactly.
Back on the side.
Exactly the same.
Feathers don't move, nothing. Look at that.
That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's a force pulling them down. Gravity.
In the three provided scenarios, each of the objects differ in mass demonstratively, and yet the acceleration due to the Earth's gravitational pull, as demonstrated by the previous video, is indeed constant. Yet, note how in each case, by the presence of force vectors, that the force is distinctly different from each other. Recall that although the feather and the bowling ball accelerated at exactly the same rate, they did not hit the Earth with exactly the same force. The bowling ball, having substantially more mass, left a crater, while the feather did not. Using a simulation, we can modify the mass of two objects in order to observe the change in the gravitational force between those two objects. It is evident the masses of the objects are directly proportional to the force being applied between them. However, the distance of the objects is not quite quite so direct. It is inversely proportional to that same force. Note, however, in what relation this inverse proportionality takes place. If the distance is doubled, the force is decreased by a factor of 4, or 2 squared. If the distance is tripled, the force is decreased by a factor of 9, or 3 squared. If the distance is quadrupled, the force is decreased by a factor of 16, or 4 squared. Therefore, the gravitational force is a function of the masses of the two objects, divided by the square of the distance between them. The capital G in this case refers to the gravitational constant, which is not important for our purposes at this time. From this relationship, let us observe certain analogies that we can make with the electrostatic force. Let us now observe a system having two charged particles with opposite charges. Note how particles without any charge exert no electrostatic force. And even if one particle has a charge and the other does not, still there is no electrostatic force between them. However, once they both exhibit a charge, there is a direct proportionality between the charges and the force that occurs between them. This applies whether charges are the same, in which case there would be a repulsive force, or if they were different, in which case there would be an attractive force. To reiterate, if the quantity of the charge between two charges changes, the force between them changes with direct proportionality. If the charge is multiplied by 2, the force is multiplied by 2. If by 4, then by 4, etc. However, we must also consider the aspect of distance. Note that if we keep the charges constant and change the distance between them, it is clear that the force between the charged particles is inversely proportional to the distance between the charged particles squared. So if we double the distance, the force between them is 1/4, or 1 over 2 squared. If we quadruple the distance, the force between them is 1 over 4 squared, or 1/16. Observe the similarity between both force equations. The gravitational force equation is dependent upon the two masses and inversely dependent upon the radius between the two objects squared. The electrostatic force equation is dependent upon the two charges and inversely dependent upon the radius between the two objects squared. The only factor that is substantially different are the constants and the units for mass and charge. Yet the symmetry in both equations is distinctly clear. The reason for this is attributable to an inverse square relationship. Recall that the surface area of a sphere is equivalent to 4 pi r squared. So why is there this inverse square relationship with both the gravitational and the electrostatic force? It is because the force is distributed radially along the surface of a sphere. The force is distributed outward from a single point in all directions, forming the shape of a sphere. And the force is thus decreasing exponentially as that force is being distributed along that surface in the area of a sphere. This is not to say that the forces, the gravitational force and the electrostatic force, are equivalent or even of the same strength. It is clear that the electrostatic force is incredibly stronger than the gravitational force, for by the ratio of their constants and using a proton, in this case, its charge and mass, uh, through their ratio, there is the electrostatic force is greater than the gravitational force by a factor of 10 to the 36th power. That's how many times stronger the electrostatic force is than the gravitational force. And it is this force, the electrostatic force, which alone holds together all matter and is the source for all chemical behavior and interactions that occur between all matter.
Photons are the packets of energy our eyes detect to see the world around us. And in the bizarre world of quantum mechanics, photons are at the very heart of magnetism. Plunging down to the subatomic level, we can see how atoms are made up of a nucleus surrounded by a cloud of electrons.
Think about the structure of an atom. There's a positive charge to the nucleus, and then the electrons have a negative charge. These two attract each other.
To explain this attraction, quantum physicists think that both protons and electrons spit out short-lived bursts of photons. Oppositely charged particles absorb each other's light, and this draws the particles together. This attractive force is known as electromagnetism.
Atoms themselves would not hold together if it weren't for electromagnetic forces.
Electromagnetism also causes atoms to stick together, to create the molecules that form us and everything around us.
Electromagnetism is responsible for the very structure of our matter, atoms holding together.
Molecular bonds in our bodies, those are bound together by electromagnetic interactions, and therefore they're bound together by light.
A universe without electromagnetism would come apart at the seams.
If electromagnetism was turned off, matter would dissolve.
Everything would just fall apart.
I could probably, with my superhuman strength, hold myself together, but the rest of you are doomed.
Electromagnetism not only holds everything together, it makes things feel solid.
When you touch something, that's the electromagnetic force as well. We have electrons in our atoms and they repel each other, and when you try to touch something, those forces keep you from actually physically touching it. The reason I don't fall through the floor is not that the floor is particularly solid. Most of the floor is empty space. It's the electric forces of the atoms in the floor against the electric forces of the atoms in my body that hold me up. Just those little forces of those few atoms are enough to hold me up against the entire gravitational force of the Earth. Electromagnetism rules.
The essential takeaways for this video is as follows. The electrostatic force is proportional to the amount of electric charge and inversely proportional to the distance between those charges. The greater the amount of electric charge, the stronger the electrostatic force between them. If between similar charges, this force is repulsive, and if between dissimilar charges, this force is attractive. The smaller the distance between those electric charges, the stronger the electrostatic force is between them. Till next time, when we consider the mysteries of the absolute,